Hey physics kids, Mrs. Campbell here. In the 6th video on thermodynamics, we're going to talk about the first law of thermodynamics. What the first law of thermodynamics is just a restatement of the law of conservation of energy. So in the past we've talked about all of the energies in the system, the kinetic and the potential, and how it gets converted into thermal energy. But when we deal with ideal gases, remember the internal energy really is the kinetic energy, because in an ideal gas there's no bonds or associations, so potential energy is 0. And remember we said that we can change the amount of internal energy in a gas by either doing work on it, so we do work on the gas and we increase the energy, or we transfer heat in, or we can reduce the energy of the gas by either taking work out, so the gas itself is doing work, or heat flows out of the gas. So for the first law of conservation, the first law of thermodynamics, it's actually the mathematical statement of this. So the first law of thermodynamics says that if I change the total internal energy of my system, I do that either through adding or removing heat, or doing work on the gas, or the gas doing work. So the internal energy is really a state function, whereas these are processes. They're the flow of energy either into or out of the system. Now, a couple things about the signs of heat and work, and we're going to get into more details also with both of these, but if we add heat, so heat flows in, or we do work on the system, we'll increase the internal energy of the system. So the amount of energy goes up. And remember that for ideal gases, that's kinetic energy. Or if we decrease the amount of internal energy, it's because either heat is flowing out of the system or the system itself is doing work. So, right, if you do work, you are using energy to do that. And it's the same thing for gases. So let's look a little more at heat and work. So heat, right, is the flow of thermal energy. So if the system is gaining heat, there's thermal energy that's being transferred in, and we call that positive Q, or a positive value of heat. Or if thermal energy is flowing out of the system, I'm losing that thermal energy, I'm losing the energy, and so my value for heat is negative. Okay? But work is the trickier one, right? Remember that work can be calculated by taking a force and multiplying by a distance. Now, if you think about it, work can be done, if we think about like a chamber of gas with maybe a movable piston in it, right? Work can be done by the gas, right? It can force the piston out. It can push it out. Right? And when that happens, it's going to lose some energy because it's actually doing some work. Or we could push that piston in, right? And if we push that piston in, we're doing work on the gas. So remember when we talked about signs of work, work was positive if the force was in the direction of motion. So if I shove you, right, I apply a force and you move, right, it changes your kinetic energy, I'm doing work on you. I'm doing positive work. What's a work that's a negative work? That's always friction, right? Friction always is a force that opposes motion. So friction always takes energy out of a system. But how does this apply to gases? Well, okay, let's talk about force in gases, right? We talk about force in terms of pressure and area. So if we rearrange this equation, force is equal to pressure times area, and I plug that into my equation and I get pressure times area times delta X. Now, we've done this with fluids too, right? A times delta X is the same thing as volume. So I'm going to change this equation and then I'm going to stick a negative in here. So work is equal to negative pressure times volume, the change in volume. Well, what does this negative do for me? Well, the negative will always help us get the right sign in our first law of thermodynamics equation. Delta U is equal to Q plus work. So let's think, that way we don't have to think as hard, right? If we think about what happens when the gas does work, right? The gas is pushing on the piston, right? And we'd say that the gas is doing positive work, But think about what's happening to the energy of the system, because now we're using work to find out how the energy of the system's changing, right? So if you are pushing on something, right, you are doing work, you are expending energy, and this is what's happening to the gas. The gas is pushing on the piston, and the volume's getting bigger, and it is doing work, which is lowering its energy. It's exhausted. So if the volume expands, the gas is doing work, but it's going to lower its energy, and that's why we put that negative in there. Then we don't have to think about it. So anytime the volume goes up, the gas is doing work, and that work is going to lower the internal energy of my system. Now, if we shove the piston in, we're doing work on the gas, and the volume's getting smaller. I'm squeezing it, and that's going to actually increase the energy because I'm doing work on the system. I'm putting energy into that gas. So that's going to make the volume smaller, which then gives us a positive value. Remember, it's always final minus initial. It's going to give us a positive value for work. So when I put that into my first law equation, delta U is Q plus W, I'm going to get an increase in the energy due to the work. So one thing we should also think about is that, these are kind of equal but opposite work. So if the gas is doing work, then the work being done on the gas is the opposite sign. So if I do work on the gas, so I'm pushing the piston in, then the gas is doing negative work. Just, well, kind of a Newton third law thing, isn't that? All right, because this is something that messes students up all the time, let's talk about this one more time. If a gas expands, right, that means the gas is pushing against the piston and it is transferring work out because it's doing work, it's getting tired. So that means its energy is going to go down. So delta V goes up. So if we put that negative sign in there, then it's going to be a negative work and we're going to lose internal energy. But if the piston compresses, which means we're actually pushing on the gas, we are doing work on the gas, then the volume's getting smaller, right? Final minus initial is a negative value for volume, but when we put that negative in that work equation, it makes it positive, which means the energy of the gas goes up because we're the ones that are putting work in. We're putting energy into that gas. So make sure you remember that and don't forget the negative. It really helps. Well, and that it's always final minus initial for volume. Now, a couple more things about this. If you think about a PV diagram then, the area under the graph is the value for work, right? Area is, on anything, right, is base times height. Right? Here's a little square or rectangle. Base times height would give us the area. And work is pressure times volume, right? Area, base times height, work, pressure times volume. So the area under a PV process is the work being done. Now, in order for a gas to do work then, right, volume must change because if delta V is 0, then work is 0. So an isovolumetric process, which on a PV diagram, remember, is just a vertical line, has no area under it, and it's great because it doesn't do any work. The other thing is that when we calculate work by using the area under the curve, we're only going to do that for isobaric processes, right? I can do a base times height on a square, or I could even do it on a triangle maybe, but I certainly can't do it on an isothermal process, right? I'd have to do some calculus here. But that doesn't mean there's no work being happening, right? Work is still happening because volume's changing. It just makes it a little more difficult for me to use this equation to calculate the work done. All right, so let's do some calculations. So I have a gas that's absorbing 400 joules of heat and at the same time is doing 120 joules of work on the piston. What's the change in internal energy of the system? Pause the video, see if you get it right. Well, the question is, what's positive and what's negative? My law of thermodynamics says that the change in internal energy is equal to heat plus work. Well, we're putting heat in, which is a positive value for heat, but the piston is actually doing work, or the gas is actually doing work, which means that that's a negative value for work. So we're putting heat in, positive Q, but the gas is doing work, which means it's expending some energy. It's increasing in volume, so that's a negative work. So now I just got to plug and chug. 400 minus 120 is positive 280 joules. How'd you do on the signs of heat and work? All right. Oh, we've seen this before, right? In our last video, we looked at this cyclic process where we had the isovolumetric process, the isobaric, and then another isovolumetric, and another isobaric. So this time I'm going to ask you a bunch of questions. And I'm going to take myself off the screen because I'm tired of looking at my face. You probably are too. So what I want you to do is find the work done in each of these processes and the net work done by the gas. Pause the video and see if you can get this correct. All right, if you said that in process 1 and process 3 the work was 0, you are correct, right? These are isovolumetric processes, so there's no change in volume. And if there's no change in volume, then there can't be work. And of course, there's no area under a vertical line. What about process 2? Now, the work done in process 2 is this entire area, the whole area under 2. Don't bother looking at 4. So our base, right, is 3 VO, final minus initial. We're going this way, minus VO. And our height is from here to here, so that's 2 PO. So it's this entire box right here. So if we plug that into our equation, remember, we don't forget the negative. So we've got our 2 PO times our final minus our initial volume, which is a positive volume change. It's an expansion. You should get a negative 4 PO/VO. Now in process 4, we have just this area under the line of process 4, and that has the same volume change, except for now it's a compression. So this is my final and this is my initial, and my height is only PO. So when I plug that into my equation, negative PO times final minus initial, and the negative volume change times the negative is positive, I get 2 PO/VO. Now what's this net work thing? Well, the net work, right, just like a net force, is the sum of all of the work being done. So I just add these together, and I get negative 4 PO/VO plus 2 PO/VO, and that gives me a negative 2 PO/VO. Now, interestingly enough, right, that is the area that is enclosed by this rectangle right here. So the net work in a PV process that's cyclical will always be the area that's enclosed by the process. All right, I got another question for you. Let's see if you can get this right. What is the net change in internal energy in terms of PO and VO? Pause the video, think about this. Now, this is a cyclic process, right? And remember that internal energy is heat plus work. But if you remember back to our very first thermodynamics video, the change in internal energy also was related to the change in the kinetic energy of the gas, right? And the kinetic energy, right, that was the 3/2 kBT thing. So if I go back to my original state, right, I started here and I ended up back here, which means I ended up back at my original temperature. So even though the internal energy, right, the kinetic energy of the gas was changing as I went through these processes, because I ended up back at the same temperature, it's 0. So the amount of heat and work must balance each other out when I get to the very end of this process. All right, last problem. So we saw this problem at the end of our last video where we had this gas that went through this isovolumetric pressure change and then went through an isobaric expansion. What I want to know is, what is the work done on the gas as it goes from process A to B and then from B to C? Then we're going to say that this process also returns back to its original state at A through this isothermal compression. And so what I want to know then also is, what is the net work? Is it positive, negative, or 0? Don't calculate it, just is it positive, negative, or 0? What about the total change in internal energy of the gas? And is the heat flow from A to C in that whole cycle positive, negative, or 0? So pause the video and see if you can answer these 4 questions. All right, well, if you said in process A to B, the work done is 0, you are correct. There is no change in volume in process A, B, so work is 0. In process B to C, we're looking at the area here under this line, this isobaric expansion. So you need to do the base, so the difference between here and its final minus initial, times the height. And remember, these are in atmospheres, so we need to put them in pascals, just like we did in the last video. And when you do that, and remember that work is the negative of P delta V, we get a negative 533 joules. So in an expansion, the gas is doing the work, which means the internal energy will go down, so we say that the work is negative. Now, if we take the gas through this entire cycle from A to B to C and back to A, the net work, well, the area under this compression, which would be this entire area all the way down here, right, that area is bigger than the expansion area, which is just this area here. So because this area, the process C to A, this compression has higher area, that means that our work is going to be positive. Now, the total change in internal energy, well, I know that delta U is Q plus W, but remember that delta U is also equal to the average kinetic energy of all the molecules of the gas, or the molecules times 3/2 kB T, or delta T. So if we start at A and we go all the way back to A, then the change in temperature is 0. So that means that our change in internal energy must be 0 too. Now, if delta U is Q plus W, and we just said that work was positive, but delta U is 0, then my total heat flow must be negative. So by the first law, in order for this to be 0 and work to be positive, then Q must be negative to cancel out all of the work that's being done. So heat must be flowing out of the gas. How'd you do? See you in class.